Hello, and welcome to the Balancing Equations, Redox, and Moles video activity. One of the key skills from this chapter is going to be balancing chemical equations. And what this means is that atoms can't magically appear or disappear during a chemical reaction. We have to have the same amount of atoms of each type of element before and after the reaction. So if we look at this very simple chemical equation right here, where a couple of hydrogen molecules react with an oxygen molecule to produce two waters, what we see is before our reaction, we actually have 4 atoms of hydrogen. And then afterwards, we still have 4 atoms of hydrogen. So we've rebonded them, but no atoms have appeared or disappeared. And similarly, we have 2 oxygen atoms before the reaction and 2 oxygen atoms after the reaction. So the oxygens, again, haven't appeared or disappeared. We need the same number of each type of atom before and after the reaction. One of the important things to remember when balancing chemical equations is you can only change the coefficients, and the coefficients are the numbers in front of the chemical formulas, and you should never ever change the subscripts. Now, why is this the case? Well, we're going to take a look at our friend Chemistry Cat over here, and he's going to give us a clue. So you have the joke here about 2 men walking into the bar, and essentially the joke is stating that H2O and H2O2, these are different compounds. So the problem here is if we change the subscripts, like they did in this one right here, then what occurs is that we actually make an entirely different chemical reaction with different reactants, different products. So this is a different chemical equation. We must not change the subscripts because then we'll end up with a different chemical equation. We must only change those coefficients. And we're going to want to make sure that we have whole number coefficients when we balance these equations. So we're looking for integer values here. So some helpful tips for when you're balancing chemical equations is that you'll notice that we'll often have chemical reactions where we produce CO2 in water. These are very common in chemistry as well as biology. And so we have the helpful hint here. If we start by trying to balance the oxygen, then that's going to lead to problems. And the reason for that is we have lots of oxygens in this equation. And if we try and balance the oxygens first, they're just going to break as we go through and balance other things. So again, if you have reactions that produce CO2 in water, then you probably want to balance the oxygen last. And these will come up quite frequently, this type of equation. And so what we have to do here is we have to go through and make these match. So we see here we have 2 carbons. And so we're going to need 2 carbons over here. So we're going to need a coefficient 2 right there. And then we have over here 6 hydrogens. So then we're going to need 3 H2O. So now we have 6 hydrogens on both sides. So now this becomes 2. This becomes 6. And if we look right here, we have over here we have 3, and then over here we have there's 3, so it's 7. So that means that we are going to need 3 O2s in order to balance this equation. And so now this becomes 7 and 7. So let's see how we did here. Did we balance this correctly? Heck yeah, we did. Excellent. So we balanced this equation correctly by changing those coefficients, and notice that we didn't change any subscripts. And I just like to go through by atom and make sure we have the same number of each type of atom on both sides of the equation. Let's look at another example right here. So another helpful tip when it comes to balancing chemical equations is if you have polyatomic ions, treat the ions as one unit. So if we're going to balance our equation right here, we want to make sure that we are going to treat the phosphates as one PO4 unit rather than individual phosphates. And the reason for this is it just simply saves us a lot of work. So looking at our equation right here, I see that we have 3 sodiums, and that means that we are going to need 3 sodiums over here. So I'm adding in a coefficient in order to make our sodiums match. And then I have 1 phosphate, and now we have 2 phosphates on the right. So I'm going to put a 2 over here, and we encounter a problem. And that problem is we've now broken our sodiums. Those are no longer balanced. So I'm going to go ahead and erase that 3 right there. And so it's no longer going to be 3. That's now going to become a 6 right here. So it takes 6 sodium chlorides to use up the 6 sodiums we have on the left side. Our phosphates are now balanced, 2 and 2. And now looking at our magnesiums, we would need 3 of these magnesium chlorides in order to match the 3 magnesiums over here. And then you'll often find the last atom is balanced. So we have 6 chlorides over here and 6 chlorides over here. So now our equation is balanced. Hurrah! And again, I highly recommend when you balance chemical equations with polyatomic ions, treating them as one unit rather than looking at them atom by atom. So I'd like you to now pause the video and please complete questions number 3 in the, questions 1 through 3 in the associated video. Alright, welcome back, gang. Let's move on to the next topic. And our next topic is what's known as oxidation reduction, or people often call it redox for short. And redox is just an abbreviation of reduction oxidation. So we're talking about oxidation reduction or redox. And so the key thing here, these are chemical reactions where electrons are transferred. And so not all chemical reactions are of this type. Many chemical reactions are not redox reactions, but many important redox reactions are. So they give the example here of corrosion reaction. So our iron rusting is an example of a redox reaction. But these are also really important in biology, and so more on that to follow. So again, redox reactions are where electrons are transferred. And so we have oxidation, and this is where we have loss of electrons. So people often use the oil rig sort of tool to remember these. So oxidation is loss, so there's our oil portion. And so our zinc right here is losing electrons. It's forming a cation. It's going from neutral charge to a cation. And our other product here is electrons. So if electrons are a product, that means that we have oxidation occurring. Now down below we have reduction. So our copper ions here are gaining electrons to become copper metal. And so if we're gaining electrons, they'll often be listed in the reactant side of our equation. And reduction is gain. There's our rig part of oil rig. So if we're becoming more positive in charge means oxidation, because we're losing electrons, becoming more positive in charge. And if we're gaining electrons or becoming more negative in charge, that's going to be reduction. And so these two things always go together. If we have oxidation, we must also have reduction, because the electrons can't just disappear. They have to come from somewhere and go to somewhere. Now I want to point out that identifying redox reactions in covalent compounds is a bit different. This sort of change in charge we looked at in the previous slide works really well for ionic compounds, but not so much for covalent. So in covalent compounds, we're going to look for things like oxidation. We'll often see loss of hydrogen and or gain of oxygen. So that's oxidation. And reduction we can often identify in biochemistry or in covalent compounds as gain of hydrogen and or loss of oxygen. And so we have an example down here where our nitrogen, in this case, is actually losing oxygen, so that's going to be reduced. So reduction right here, boom, we have our N2O that's losing oxygen, so that's being reduced. And our compound right here, this is actually octane right here. Our octane is being oxidized. It's gaining oxygens to form waters in CO2s. And we might also see in biological systems, you might be wondering, well, why the heck do we breathe air? It's so we can get this oxygen. So oxygen is commonly involved in redox reactions, but not always. But anywho, if you're wondering how we use the oxygen we breathe, we use it to oxidize the food that we eat. So here's where things get kind of confusing. Redox is tricky stuff. And so we also have what's known as the oxidizing and reducing agent. And so our reactant that is oxidized during a reaction is referred to as the reducing agent. And you might be saying, well, why in the heck would that be the case? Well, the reason is if something's being oxidized, it's losing electrons, right? So when it loses those electrons, they're going to be used to reduce the other chemical. So again, the reducing agent is oxidized and gives its electrons away to another chemical to reduce that other chemical. And our reactant that is reduced during a chemical reaction is known as the oxidizing agent. Well, where does this come from? Well, it's because the electrons that it takes or it gains, it's stealing from another chemical, helping to oxidize that other chemical. So I'd like you to now please pause the video and complete questions 4 through 6 on the activity. And this video will be completed or concluded in part 2. So we'll continue in part 2.